Today we want to talk about the fundamental theorem of calculus and go over that, and then start getting into more details about this finding antiderivatives business. So, the fundamental theorem of calculus requires just a continuous function on a closed interval, and there are two parts to it. The first part that we saw in chapter 5 is that the definite integral from a to b of f of x to x is capital F at b minus capital F at a, where capital F is an antiderivative of f. So the first part says you can use an antiderivative to calculate a definite integral. That's what we're saying in the first part. Part 1, you can use an antiderivative to calculate a definite integral. So part 1 says use an antiderivative to calculate a definite integral. That's what we conclude from part 1. We can use an antiderivative to calculate a definite integral. Part 2 goes the other direction. So part 2 says we can use a definite integral to construct an antiderivative. So really these two parts are just saying definite integral, antiderivative, put them together. Part 1 says use an antiderivative to calculate the definite integral. Part 2 says use a definite integral to construct an antiderivative. Part 2 is useful because calculating a definite integral comes down to calculating area. So these two really are stuck together. It's always listed as two parts, but they're really kind of stuck together. They tie definite integrals and antiderivatives together. The reason that this is good, especially the second part, is that calculating definite integrals can also be done by calculating area. And for that, all we need is length times width and lots of data. So this is good. This is good because all we need to calculate a definite integral, oops, I left something out there. Is area equals length times width. And lots of data. For the problems that we did, that lots of data amounted to like 5 whole points on the curve. But we were calculating it's somewhere between 300 centimeters and 450 centimeters, which is not a very good approximation. But it's the idea is what's important. It's good that we can construct an antiderivative using the definite integral because the definite integral is just an area calculation, and area is just length times width plus lots of data. Any questions? It still is a thing that we want to do. A thing that we still want to be able to do is find antiderivatives when we can. The reason that it's important to be able to construct antiderivatives is that there are some functions that do not have what I call nice antiderivatives. So this is important Because there are some functions that do not have nice antiderivatives. There are some functions out there, functions that we care about, that do not have nice antiderivatives. What that means is that the function is not the derivative of some finite combination of elementary functions. This is why I say nice instead of finite combination of elementary functions every single time, because that gets to be too much. So by the word, when I say nice antiderivatives, that is some functions are not the derivative of a finite combination of elementary functions. Some functions out there are not the combination, or sorry, not the derivative of any finite combination of elementary functions. Finite just means there's a finite number of terms. Elementary functions are all the functions that you've encountered so far. That's a pretty strong assumption to make based on your mathematical history, but most of the functions that you've encountered so far are elementary functions. Your polynomials, your radicals, your rationals, your trig functions, your inverse trig functions, your log functions, your exponential functions. Anyone do the hyperbolic trig functions?
Yep.
My class is like, oh, no, we totally didn't do that. I think I mentioned it exactly like one time and then let it go. All right, so that's why it's important to be able to construct antiderivatives, because there are some functions out there that they're just not the derivative. They don't have nice antiderivatives. They're not the derivative of a finite combination of elementary functions. To write those antiderivatives, we would need either an infinite combination or we'd have to use non-elementary functions. And non-elementary functions would be functions really that we construct. So here we are constructing a non-elementary function in some cases. If little f does not have an antiderivative, then when we construct a function this way, that'll be a non-elementary function. Any questions?
So this might be kind of goofy, but so derivatives are the rate of change. What is the antiderivative?
Antiderivative we usually think of, the way we usually frame it in Calc 1 and Calc 2 is to say the derivative is the rate of change. And when we're finding an antiderivative, we start with the rate of change and we're getting back to the function. So we integrate the velocity and end up with the position.
Gotcha. Okay, thank you.
So if we look at the units, if we integrated, say, a position function with respect to time, the units would be, say, meters for the position multiplied by seconds for the dt. So our units would be meter seconds. So that could have useful applications. Like we do have units that are like that, like person hours. How many person hours is something going to take? Where that's like a combination that way. But our usual road in, because this is pretty much an engineering class, is that we start with the relationship between position, velocity, and acceleration. We differentiate the position to get the velocity. We differentiate the velocity to get the acceleration. Then we go back. We integrate acceleration to get velocity. We integrate velocity to get position. we tend to not integrate position. But we could, and we just have to think about what the units would indicate. Any other questions? That's a good question. I like that one. And the answer is, I don't know. What do the units tell you? So we can also, if we limit that to definite integral, we sometimes say the definite integral of a rate of change is the total change, but we still need to invoke that the thing that we're integrating is a rate of change. So that's very hand wavy and a way to dodge the question. I'm not on camera, but I want you to know that when I said the word dodge, I actually moved off to the left to get out of the way of the question. I had to physically get out of the way of the question. All right. So all this, it's still important to be able to find antiderivatives. So we still care about finding antiderivatives, even though we can always just appeal to the second derivative and build it. So elementary functions are all the functions that you've seen so far. So an example of a function that does not have a nice antiderivative. So for example, I'm going to give you my favorite example. If I look at f of x is e to the minus x squared, this does not have a nice antiderivative. This does not have a nice antiderivative. That is to say, this is not the derivative of some finite combination of elementary functions. But we can construct an antiderivative using the second fundamental theorem of calculus. So we can't write some nice closed formula, nice simple explanation, a nice simple closed formula like e to the minus x squared over negative 2x. You can't use the quotient rule that way. You can't just unchain rule when the insides are not constant. So we can't write a nice function, but we can construct one using the second fundamental theorem of calculus. We can construct one using the second fundamental theorem of calculus. So what we mean when we say that we have constructed an antiderivative is that I have built a function that I can evaluate anywhere I expect the function to be defined. So if I wanted to calculate, say, f of 3, if I wanted to calculate f of 3, we integrate from 0 to 3 of e to the minus t squared dt. And we can just use a machine to do that. So I just grab my calculating machine, and I want to integrate from 0 to 3. So whatever we're plugging in, we just integrate mechanically. So let's see, e to the minus x squared with respect to x from 0 to 3. 0.8662. So we can evaluate this function anywhere. We don't have a nice formula. We can't write a nice formula where it's just the sum of a bunch of functions that we've seen before. We either have to write an infinite string of functions or an infinite sum of functions, or we have to write something weird like this. So we either need an infinite number of terms or we need to use some strange functions like constructions. We can even ask the calculator to graph this function if we want. Oops, I got a bunch of other stuff here. We can even do your calculator can graph numeric integrals. It's just going to be hilariously slow because the processor is not very strong. Notice that your calculator doesn't need dummy variables like integrates from 0 to x f of t dt. Your calculator seems to be okay with the being John Malkovich thing. Window, oops, my window's all messed up too. Let's see if it does it. So you can see the calculator's struggling to make these calculations. So once again, finite combination means we have to have a finite combination just means we have a finite number of terms. X squared plus 3x plus 5, that's a finite number of terms, things separated by a plus. So that's the combination that we're talking about. Elementary functions is all the functions that you've encountered so far, with the exception of the function that we just constructed with the second fundamental theorem. So like e to the minus x squared, your exponential functions, your logarithmic functions, your trig functions, your inverse trig functions, polynomials, rationals, radicals, those are all elementary functions. It's going to take a long time to get through this calculation.
So what does that 0.866 represent?
That's the value of this function when f is equal to 3. So here I am graphing the antiderivative. And if we plug 3 into this function, that's the antiderivative of e to the minus x squared when x is equal to 3. I can't hit trace yet because it's not done drawing the function. Because the processor is like,
How come you put e to the minus x squared instead of e to the minus 3 squared when you would, because that's what you would normally do in the
That's what I would do if I wanted to calculate the specific value of the function when x is equal to 3. So here I'm trying to graph the antiderivative of e to the minus x squared. So if I just put the 3 in there, I would just graph the value of the function. And that's not what we're trying to do. I wanted to be able to evaluate the function a bunch of times. So once I'm looking at the graph, I can plug in 2, and then 1, and then 7. Oops, I'm out the range. So here I am looking at all the values of the antiderivative of e to the minus x squared. Here we are just evaluating this function at one point. It's the difference between graphing x squared. Here's the graph of x squared. But if I just calculate f of 3, I come up with 9. So the reason I wanted to, the reason I entered the function this way, I want to evaluate it at all the points x. This is where this is what we're plugging in. Just like this is what we're plugging in for x squared.
But I mean, when you wanted to find out, I get that part, but when you wanted to find out the 0.886, wouldn't we normally integrate from 0 to 3 e to the minus 3 squared dx?
No. We have to integrate the function at all the values, but we have to plug in, we're not just plugging in 3 for t, we're plugging in 3 for the x. We're plugging in all the values from 0 to 3 into this function. We have to evaluate e to the minus t at 0, and then all the real numbers between 0 and 3, and we're adding up all those values.
I have an even dumber question, though. I'm kidding. How did you set the calculator to that notation?
Oh, the antiderivative notation, or the numeric integral notation, is in the math menu. And it's just down here at the bottom, FNINT.
Yeah, I get that one, but it brings up, it uses the integral symbol.
So yours is on in the mode. Yours is on this mode called math print. So if you turn on math print, then oops, quit. There we go. Then we have to put it in like we would write a definite integral. So we don't have to learn the single line syntax. So I'd go from 0 to 3 of e to the minus x squared dx. And it would give us the value. It just displays it differently.
I see.
I've always been kind of a single line syntax kind of dude, so I'd be like, oh, nah. And then, let's see, entry. So I've always preferred single line syntax when I'm talking to machines.
Thank you. And Heather, I did not mean to imply that your question was dumb. Mine is.
No questions are dumb. If you don't know something, the whole reason that we are here is so we can get our questions answered. So
if I'm understanding this correctly, you're saying that the 0.866 is just the value of the y when x is 3?
yes. Just like if we find the antiderivative of some other function and plug in a value. It's just that this is how we have to do it, because when we say find the antiderivative of e to the minus x squared, we're like, oh, well, we have to construct it. We don't have a nice answer for that.
So where did we get 3? They gave it to us.
I just made that up. I said I have to evaluate this function somewhere.
Okay.
Any questions? Any other questions? Rad.
I got a question.
Yeah.
Oh, Professor, are these notes, are they on Canvas afterwards?
Yes.
Okay.
They're in the files section.
Okay, thank you.
So when you find, like, if you were to take this and find the derivative of it, you'd be finding the rate of change. And then when you take the antiderivative, you're finding the values?
Yeah.
Okay, got it. Thank you.
Yeah, so remember what we're defining, f of x is the integral from 0 to x of, say, e to the minus t squared dt. So this is an antiderivative. Of f of x equals e to the minus x squared. So this is an antiderivative of e to the minus x squared. What that means is that if I take the derivative of capital F, since this is an antiderivative, if I take the derivative, that'll just get me back to where we started.
Okay, got it.
Any other questions? Lots of questions is the correct answer, incidentally, because we are doing a very weird thing. Every time you've encountered a function in your entire mathematical career since you started talking about functions, we've just written down some formula for what to do with the x's. And it's been always just like, oh, we just plug the x in here. If I plugged into the derivative here, plug the 3 in here, 3 gets squared, change the sign, e to the negative 9, no problem. It's been a set of rules that we just, and the formula is always very clear. We know exactly what we're plugging in. Now we're hiding that behind all this machinery that goes into building a definite integral. And so if you're watching all this and saying, this looks weird, that is the correct answer. The first time you encounter this, this looks weird.
Yeah, it's kind of that linear thinking you were talking about, right? When you're just solving for x, and then now you're trying to find different graphs from the equation.
Yeah, you're trying to evaluate a function, and your life so far has been evaluate this function, and you can see everything that's going on in the function. Now you can't see what's going on in coming up with that function, and so it's weird, and your mind is like, oh, whoa, this is weird. So thinking this is strange is the correct answer.
Need more caffeine.
Then the question becomes, is there enough caffeine to even make this work?
Probably.
All right, so let's go on to some simpler things. The important thing to walk away from this, at least today, the important thing to take away from this is that if we have a continuous function, there is an antiderivative. It might just be we have to construct the antiderivative. So let's switch our attention to finding some antiderivatives that we can actually find. So let's switch our attention to finding antiderivatives. That we can actually find. So what we're going to be talking about here are techniques of integration. Finding antiderivatives, another word for that is integrating. So we're going to be looking at techniques of integration. So this is where the fun part happens. This is the part we're going to spend a whole ton of time on. And this is the part that I said at the top of the class, you're not going to have to do after calculus. But doing techniques of integration after calculus is not the point. And I think I've mentioned it before. If you're in your job at SpaceX and you're about to find an antiderivative by hand, you are about to get fired. Unless your boss says, hey, my kid is in calculus, can you tutor him? And you're like, oh, yeah. And he's like, oh, can you do it for free? And you're like, oh, aren't you a millionaire? And he's like, oh, yeah, but I got to be a millionaire because I'm cheap. And then you do it anyway, because we call that internships, which is kind of a fancy name for slaves. But don't think about it too much. Just take the crumbs that they give you and say, thank you, can I have another? And then the answer will be no, you cannot have another. So let's switch to finding antiderivatives that we can actually find. What we're going to do is we're going to take all the derivative rules that we learned in Calc 1 and reverse them. So let's reverse all the derivative rules we learned in Calc 1. Because antiderivatives is just the opposite, the inverse of finding derivatives. So we're just going to reverse the previous class. We're going to reverse all the derivative rules we learned in Calc 1. When you learn math, you have to learn it backwards and forwards. So here we are, learning what we did backwards. Got to learn it backwards and forwards.
Yes, the transitive property of integral.
Kind of, yeah, it's more, I think it's, what is it called? Is it reflexive? Or A equals B, then B equals A. Anyway. I do wonder sometimes if we're not just doing the transitive property of suffering when we teach this. Symmetric, thank you. If we're not just doing the transitive property of suffering. It's like, oh, well, I had to suffer, so I'm going to have to pass that suffering on to my children. So I don't know, maybe there's a way around this, because calculus is like, oh, dude, I'm technology from the 90s and I can find antiderivatives, at least numerically. And then phones will come along and say, oh, dude, you have access to the internet, and the internet can totally find these things symbolically. And then teachers like, oh, get out of here, technology. We're going to do things by hand. And then technology collectively sighs. Maybe that's how we hold off the robot apocalypse. I don't know. I'm just kidding. We can't hold off the robot apocalypse. We're building it ourselves as we speak. Let's switch to finding some antiderivatives that we can actually find. What we're going to do is reverse all the derivative rules we learned in Calc 1. So let's take a look at our favorite derivative rule, the power rule. If I want to find the derivative of, say, x to some power, what's the derivative of x to the n? Now we're trying to figure out how to type it in the chat. So we bring the exponent in front.
N minus 1.
Yeah, nx to the n minus 1. We're like going to type it in chat, then we're like, oh, forget it. Let's just hit the space bar and speak it. Thank you. So the derivative of x to the n is nx to the n minus 1. To type it in the chat, oh, perfect. To type it in a single line, we have to say to the, and then parentheses, because there's lots of extra stuff in our exponent. So take a look at what we're doing to make this calculation. First, we multiply by the exponent, then we subtract 1 from the exponent. So the order of things that we did, we multiply by the exponent, and next we subtract 1 from the exponent. That's the order of go to get there. Multiply by the exponent and then subtract 1 from the exponent. So to turn this around, to go the other direction, if we want to integrate an x to the n, let's write down our notation for an indefinite integral. Let's say integrate x to the n dx. So here is an indefinite integral. It's not from a to b, it's just integrate x to the n. So this is an indefinite integral.
Are indefinite integrals the same thing as an antiderivative or no?
Yes, they are.
Got it.
Find the antiderivative. Oops, not the an antiderivative. So here's an indefinite integral. And what we're going to do is undo the two things that we did before. So the last thing that happened is subtracting 1 from the exponent. So the first thing that has to happen is we add 1 to the exponent. And then the first thing that happened in the derivative case is to multiply by the exponent. So now we have to undo that by dividing by the new exponent. So 1 over n plus 1, x to the n plus 1 is the antiderivative. And in single line syntax, as it shows in the chat, 1 over, you need more parentheses. That 1 over n plus 1, it's 1 over not just n plus 1, it's 1 over n plus 1. Technically, you can get away with not putting parentheses around the fraction 1 over n plus 1, because we've divided by n plus 1, and then we can say x to the n plus 1. But the internet, specifically social media, has taught us that this is a poor idea. Even though this is 1 divided by the sum of 1 and n, and then multiply by x to the n plus 1. So for clarity, we should include more parentheses. We should put this in parentheses for clarity. So these parentheses here. Now we have removed all doubt about where that x is. That x is definitely in the numerator now. We could totally just type this by saying x to the n plus 1 over n plus 1. So we could say x to the n plus 1 over, well, I'll still need these, n plus 1. But now we have another problem, because in the order of operations, division would take place before exponents. So now the parentheses around the base are necessary. Or sorry, the parentheses around the numerator are necessary. Writing things in a single line sure seems like a pain, but if we would all practice writing things in one line with all the parentheses that we need, I promise you we would be better at algebra. We would also not fall for those stupid Facebook posts where someone says, what's the answer? And like half your friends are saying 9, and the other half of friends are saying 1. And then they start bringing up things like PEMDAS and BODMAS, and every single one of them is getting the thing wrong. Because someone posed a question to start a fight and everybody fell for it. So when someone posts one of those order of operations problems, that's trolling. Someone is out there trying to start a fight. Don't fall for it. Just don't ask the question. Just post a reply that says, why are you trying to start a fight? What's wrong with you? It's rude. Trying to start a fight amongst your friends, people you call friends. So don't fall for that crap. Because the fact is, all those expressions are designed to be unclear, and whether or not there's technically a right answer is irrelevant. All those order of operations questions can be fixed, and clarity can be installed by just putting in parentheses. Ask for clarification. Don't fall for the trolling. Say, oh, do you mean this one with these parentheses or this one with this set of parentheses? Anyway. So anyway, this is our new thing. Our first rule for antiderivatives is to add 1 to the exponents and divide by the new exponents. Tomorrow, we're going to expand our list of antiderivatives that we can actually find. We should have a plus C, but we'll talk about that tomorrow. I did just say find an antiderivative, and that certainly is one of them. When you write plus C at the end, you're finding the general antiderivative. But there's no need on the first day just to go all the way up the chain of command like that. All right. That's going to be it for today. I will see y'all on tomorrow, and we will find some more antiderivatives, and it will be super fun.
Thank you.
Thank you.
Thanks for playing, everybody.
Thank you.
See y'all tomorrow.
Bye.
Thanks for playing.
Thank you.